Hi guys, welcome back to another statistics video. If you're new here, my name is Brittany. I'm a teaching assistant in the Department of Industrial Engineering at the Georgia Institute of Technology, and I just make videos on probability and statistics fundamentals. So today we're going to talk about how we describe probability distributions. I'm going to talk specifically about discrete populations, and in this case we're not going to be talking about sample stats. We'll be talking strictly about population statistics. And so we can use numbers, or in this case statistics, that could best represent or try to tell some kind of story or summarize a diverse, larger set of data. So let's run through a couple numbers or stats that we can use to describe this. The first one is a mean. This is a measure of central tendency of a probability distribution, and in this case for our discrete population distribution. And we can represent mean as the Greek letter mu, or also as an e of x function, where x is our random variable. And this is equal to the equation where we can take sigma for all x, so we'll sum this equation for all our random variable x. We'll multiply the value of our random variable for that instance by its probability mass function, which is a little f of x function. And so just to reiterate, this is for our random variable, which is represented by a uppercase letter x, and our probability mass function, which is represented by an f of x function, which is equal to the probability of our random variable x being equal to some instance of that random variable. Secondly, we can describe a probability distribution using variance. And variance is a measure of dispersion, or a measure of the variability of a probability distribution. And so we can denote variance as sigma squared, or also as a v of x function, where x again is our random variable, or our discrete random variable. And it's also sometimes written as var, or var of x. And the equation for variance is written as e of our random variable x subtracted from its mean, all squared. And if you just break this down, we find that it's equal to e of our random variable x squared minus the mean squared, where mu is representing our population mean. And thirdly, we can also describe a probability distribution using standard deviation, which is a measure of dispersion. And so this is denoted as just the symbol sigma when talking about a population distribution, also sometimes written as st.dev for short. And the equation for this is just the square root of the variance. In other words, the square root of sigma squared is just sigma, which is our standard deviation. All right, let's move on and talk about some properties of mean and variance. So firstly, properties of mean. So let's say for a and b are constants, and for x and y are our discrete random variables. We can say that a couple statements are true. Firstly, that if we take the mean of x plus y, we can break this down and redistribute it. Secondly, we can also say that if we have certain instances for our discrete random variable x, for example, from x sub 1, x sub 2, all the way to x sub n, we can say that this is equal to the mean of e of x sub 1 plus e of x sub 2 all the way to e of x sub n. We can just add all of those individual means together, and that is an equivalent statement. Thirdly, we can also find the mean for an equation that contains constants and coefficients, and we can redistribute the coefficient outside of the mean. And we can also say that the mean of a constant is just the constant itself. In this case, the mean of our constant b would just be equal to our constant b. And as a fourth statement, we can also say that if we take the mean of a random variable squared plus another random variable, we can redistribute that and say that this is equal to the mean of that first random variable x squared plus the mean of the random variable y. And we can solve for those two means separately, then add them together at the end. All right, let's move on and talk about properties of variance. So we can say a couple statements are true, again, for our constants a and b, and for our discrete random variables x and y. Firstly, if we have the statement for finding the variance of our random variable x with the coefficient of a plus the constant b, we can take the coefficient a outside of the variance and square it, then multiply it by the variance of the random variable x itself. And we can also say that, moving on to our second statement, which is also applicable to the first, that the variance of a constant is equal to 0. So for example, the variance of b would just be equal to 0. The variance of a would also just be equal to 0. And thirdly, to expand the first and second properties, we can say that if we're taking the variance of different instances for our constant a and for our random variable x, for example, x sub 1, x sub 2, all the way to x sub n. We can redistribute the equation, take the coefficients of a sub 1, a sub 2, all the way to a sub n, take them outside of the variance and square them, then multiply them as coefficients by the variance of our instances of x. So in this case, x sub 1, x sub 2, all the way to x sub n, and we can add those individual components together. And just to reiterate, when we take the coefficients outside of the variance equation, we'll have to square them, and also that the variance of a constant is 0. All right, let's move on to an example. So let's say that we have the probability mass function, or for short, the PMF, for a discrete random variable as follows. Let's just write out this given PMF that we might have. And firstly, before we do anything with this, let's just note a couple things as review for what a PMF is. So a probability mass function is a little f of x function with a lowercase f of x, in which f of x is equal to the probability of our random variable x being equal to some instance or some case of x. Secondly, a PMF expresses a probability distribution of probabilities when our random variable x is at or equal to a specified x value. So x sub 1, x sub 2, all the way to x sub n, however large our range is for our random variable x. And thirdly, we can say that this is a valid PMF because these two statements are true. Firstly, that all values for our little f of x function, in other words, our probability that our random variable is equal to a given instance within the range, all those values are non-negative. So they're either equal to or greater than 0. Secondly, we can also sum all the values of our f of x function, or sum all these probabilities together, and that should equal the total probability, in other words, 100% or 1.0. And since this statement is also true, we can call this probability mass function valid. And if you'd like to see more examples on that, you can go check out my old video, which I'll link somewhere here or here. So to make this more of a realistic example, let's just say that our random variable x represents the number of people at ballroom dance lessons, where you can't come alone, you must have a partner, and the 2 instructor pair is always going to be there. So our range begins at 2 and it counts up by even real numbers all the way to 10, which is the total capacity for our ballroom dance class. So let me pose a question. Let's find the probability that exactly 3 couples show up. So 3 couples would be 6 people, so the probability that our random variable x is equal to 6. Well, we can look back at our probability mass function, see where the probability that our random variable x is equal to 6 is just 0.31 or 31%, and this is the probability that exactly 3 couples or exactly 6 people show up, no less, no more. All right, so let me pose another question. Let's find the mean number of attendees who come to lessons. So our mean would be an e of x function, also denoted as the Greek letter mu. And as we saw earlier, we can use the equation for all random variable x values. We'll take that random variable x and multiply it by its respective f of x function, or in other words, its respective probability. So just to write this out, it'll be equal to the equation for our first component, being our random variable x equals 2, multiplied by its respective probability, 0.17. And we'll do this for each component. So our next one is 4 multiplied by its respective probability, or its respective f of x function, which is 0.29. And we'll do this for each component and sum them together, and we'll find that we get 5.64. In other words, this is our mean number of attendees who will come to lessons. All right, let me pose another question, and let's find the variance of this probability distribution. So variance we can denote as a v of x function, or sigma squared, and this is equal to the equation e of our random variable x itself squared minus the population mean squared. And so the way I would approach this would be to first find e of our random variable x squared. And so this would be equal to the function pretty similar to actually the function for a mean, except instead of just leaving our random variable x, we're going to square it. And so for our first component, we'll see that we have x equals 2, and we'll square this value since we're squaring all our random variable values, and we'll multiply this by its respective probability, 0.17. We'll do this for the next component, in which our random variable value is equal to 4. We'll square that value, multiply it by its respective probability, which is 0.29, and we'll do this for each component. Just solve this out and we'll find that it's equal to 39.12. But this is not our answer for variance yet. This is just one component of it. Secondly, we'll find the value of our population mean squared, or our mu squared. And luckily, we already found mu from our previous question, which is 5.64, so we'll just square that value. And thirdly, we'll solve for the actual variance, since we have all the components that comprise that function. And so we'll just plug them in, solve it out, and see that that is equal to approximately 7.3104. And lastly, let me pose a question. Let's find our standard deviation. So we know earlier standard deviation is represented by sigma, and in relation to variance, which is sigma squared, we can find our standard deviation by just square rooting the variance. So the square root of 7.3104 is approximately 2.704, and that's our standard deviation for this population probability distribution. All right, and that's pretty much all for today. Thank you so much for coming back to another video, and I'll see you next time. Bye.